In the first two lectures on kinematics of nuclear reaction, we have till now defined the Q value of the equation. Actually, in second lecture, we have solved and get the general solution of the Q value equation. You know, the general equation for Q value is given as this capital Q is equal to Ey into 1 plus my by my minus Ex into 1 minus mx by my minus 2 over my into a square root of mx into my into Ex Ey into cos theta. In fact, in this equation, this capital Q is the Q value of the reaction and Ex is actually the kinetic energy of the projectile and Ey is the kinetic energy of the emergent particle. And this small mx is rest mass of the projectile and my small my is the rest mass of the emergent particle, and this capital My is rest mass of the daughter nucleus, and theta, this is the angle at which the emergent particle actually moves with the original direction of the incident beam. Now this equation which you are seeing here can be put into a proper form in which it is expressed as a quadratic equation in root over Ey. And when we have discussed in second lecture that this equation is expressed in the form of a quadratic equation in root over Ey, then we have found that root over Ey equal to p plus minus root over p square plus q. And in this equation, what is this p? P has been defined in this way. This p is equal to root over mx my into Ex into cos theta divided by my plus my, and q is equal to q my plus my minus mx into Ex over my plus my. So this was the important result which we have found in the second lecture on this chapter. Now actually we want to discuss the energetics of the nuclear reaction. In fact, in second lecture we have discussed one of the important nuclear reaction, and that was actually exo-ergic reaction. Now in this lecture we are going to discuss the endo-ergic reaction. You know, in case of an endo-ergic reaction, the Q value is negative. So for endo-ergic reactions, Q value of the reaction is negative, and in case of exo-ergic reaction it was positive. Since Q is negative in this case, so you can see that when kinetic energy of the projectile, which was you have seen reaction was like this, x plus small x equal to capital Y plus small y. Here x represents the projectile and this capital X is actually the target nucleus which was taken at rest, and this small y is the emergent particle and capital Y is the daughter nucleus. So when we take that the projectile has a kinetic energy tending towards 0 when Ex is 0, or you can say Ex tends to 0, then you can see from this equation you can see from equation A that if Ex is 0, then see the expression for P. Since expression for P contains Ex, so when Ex will be 0, P will be 0, and then what will be this Q? So you can see in this condition Q is equal to what? Q, see the expression for Q. Q will be QMY plus QMY plus MY minus MX into EX, but we have taken EX as 0 and divided by MY plus MY, and in this condition you can see that this term is 0, so this will be simply QMY over MY plus MY. Now you can see, as in this case, that is in the case of endo-ergic reaction, this Q is negative, and if Q is negative, it means what? This Q will be also negative, and so we can say that the term P square plus P square plus Q will be also negative, because P is 0 and as Q is negative, so P square plus Q is simply Q, and that Q is negative. And if Q is negative, then what will be actually the value of root over EY? You can see from that result. And therefore root over EY, this will be actually root over minus negative quantity, and you know a square root of a negative quantity is imaginary, and so we can say that this root over EY is imaginary. And since root over EY is imaginary, so you can say that these reactions are not possible even in principle, because to proceed the reaction, the kinetic energy of the emergent particle must be either 0 or greater than 0, because kinetic energy can never be imaginary or negative in practice. So this result implies that the reaction will not proceed, or you can say this reaction is not possible. So the reaction is not possible. But we have seen in case of exo-ergic reaction that when EX was 0, then a reaction proceeds. But in case of endo-ergic reaction, if the kinetic energy of the projectile is 0, then the reaction does not initiate, or even in principle you can say this reaction is not possible. So definitely the smallest value of EX for which the reaction will be initiated cannot be 0, but this will have some finite value. Actually, the smallest value of EX, that is kinetic energy of the projectile, at which the reaction is just initiated, is known as threshold energy. So now we will define a very important term which is called threshold energy. Threshold energy. As you know, you have certainly studied in photoelectric effect, whenever an electromagnetic radiation is incident on a metal surface, then photoelectric effect just takes place when the frequency of the incident radiation is just equal to threshold frequency of the metal on which the radiation falls. Just like that, in this case, that is in the case of endo-ergic reaction, this reaction will be just started or just initiated only when there will be a minimum energy which is not zero in this case, and that minimum value of energy for due to which this reaction is just started is known as threshold energy. So we can say this threshold energy is what? This is the smallest energy, smallest energy of the projectile. When you say energy, it means kinetic energy of the projectile, Ex. The smallest energy of the projectile, that is Ex, at which the endo-ergic reaction is just initiated, is called threshold energy. Actually, the purpose of this lecture is to find the value of the threshold energy, and you will see that the value of this threshold energy actually depends on the value of theta. So we will actually properly discuss the threshold energy in two conditions for two particular values of theta. One will be theta equal to 0 and the another will be theta equal to 90 degree, because practically we set the detector to detect the emergent particle when theta equal to 0 and when theta equal to 90 degree. So in this theory, we will actually find the threshold energy in these two conditions. So now let us see that Ex is not 0, and so Ex will have any value. Let us first think that the value of Ex is large enough, and so that the value of the quantity P square plus Q is just equal to 0, because you have seen that when we take Ex equal to 0, then P square plus Q is negative. So when Ex increases, then the value of P square plus Q will actually increase and it will become 0. So when Ex has a such value that this term P square plus Q is equal to 0, let us consider that situation. So let Ex has such a value, so that P square plus Q is equal to 0. Now we know the expression for P and Q. You have seen here P and Q is defined in which manner? We have actually defined the P and Q in this manner, that P is equal to this much and Q is equal to this much. So let us now substitute the value of P and Q in this condition, that is P square plus Q is equal to 0. We will substitute the value in this equation. So substituting the values of P and Q. When we will substitute the value of P and Q, what will be our result? You know, P is root over mx my ex over my plus my into cos theta. So p square will be what? This will be mx into my into ex over my plus my whole square, this is capital Y, and cos square theta, and plus q, and q is qmy plus ex into my minus mx, my minus mx over my plus my. This is capital Y, and this will be equal to 0. So this is equal to 0. Now let us simplify this result. Let us take the LCM, which is my plus my whole square. So this result will be what? This is simply mx into my into ex into cos square theta plus, here actually there will be qmy plus ex into my minus mx into my plus my plus my, and this will be equal to 0. Now we can see from here that we can arrange the term. You can see here that first term contains ex and the last term also contains ex. So let us take this ex as a common factor. So what will be our result? This will be mx into my into cos square theta and plus my plus my into my minus mx and we take ex as a common factor, and if we bring this term qmy into my plus my in right hand side, then this will be minus q into my into my plus my plus my. Now from this equation we can find the value of this ex. Actually this value of ex is when theta is actually equal to theta. So we write this as tx at theta. So therefore we can find that the value of ex when theta is equal to theta, you can see this will be actually minus q into my into my plus my over mx into my into cos square theta and plus my plus my into my minus mx, my minus mx. Let us simplify the RHS to some extent. So this is minus QMY into My plus My and divided by Mx My into cos square theta. Here we will multiply this factor My plus My by My minus Mx. So after multiplying these two factors, what will be our result? You can see this will be My square minus My Mx plus My My and minus Mx My. This is after multiplying My plus My by My minus Mx. Now you can see this Mx My is contained in the first term of the denominator and also in the last term. So we will take this Mx into My as a common factor, and after taking this as a common factor, what will be our result? Actually, you can see our result will be Ex when theta is equal to theta. This will be minus QMY into My plus My over. So this will be My square minus My into Mx plus My into My, and if you take this minus Mx into My as a common factor, then in the last term there will be 1 and in the first term there will be minus cos square theta. Now let us take the My in denominator as a common factor. When we will take My as a common factor in denominator, then that My will be cancelled out from the My in numerator, and so the result for Ex when theta is equal to theta will be simply minus Q into My plus My over. This will be My, one My will cancel out, and this will be simply a small My, and there will be minus a small Mx, and since this last term does not contain My, so we will divide it by My, and you know 1 minus cos square theta is sin square theta, so this will be minus Mx into My divided by capital My into sin square theta. So this is actually our result in general for the threshold value of the energy, because we have found this result by taking P square plus Q equal to 0. So this, in this condition, Ex has the minimum value for initiating this reaction. So this equation A actually defines the threshold value of the energy, and when theta is equal to theta. Now we know that actually if we want to find the value of Ex which is actually minimum, then you can see as this expression for Ex depends on sin square theta, that is, you can say it depends on theta. So if we will take theta equal to 0, sin square theta will be actually 0, and the minimum value of sin square theta is actually 0, and here before this term there is minus sign, So if you will take the minimum value of this term, then this denominator will be actually maximum, and when you will divide the numerator by maximum value of the denominator, you will get the minimum value. And so to find the minimum value of Ex, we should take theta equal to 0, and then the value obtained for Ex will be actually the threshold energy. So you can see at theta is equal to 0, this sine square theta will be 0, and this is its minimum value. And so Ex of theta equal to 0 will be minimum, which is called threshold energy, which is called threshold energy. So now we denote this Ex of theta as Ex TH. This TH denotes actually the threshold energy, and so you can take sine square theta in above expression and you will get the expression for Ex TH. So what will be this? This will be simply minus Q into My plus My over My plus My minus Mx. So this is the expression for the threshold energy, that is the minimum energy to initiate an endo-ergic reaction when theta is equal to 0. So this is the expression for threshold energy. Now actually we will express this expression for threshold energy in terms of the rest masses of the projectile and the target nucleus, because you can see this expression is in terms of the rest mass of the daughter nucleus, the emergent particle, and the mass of the projectile. But now we want to change this expression in terms of the mass of the projectile, that is you have considered that a small x is projectile, and the mass of the parent nucleus, which I have denoted by this capital X. So, and this a small x has mass mx, and this capital has mass M capital X. So our aim now is to express this expression in terms of these two masses. And for this we will see the definition of the Q value of the nuclear reaction, which we have discussed actually earlier in the previous lectures. So you have seen that as Q is equal to, we have defined the Q value of the reaction in this manner. This is equal to mx plus small mx minus my plus small my into c square. And from here you can easily find the value of mx plus small mx. You can see this expression. This will be actually equal to my plus my plus q by c square. This is mx plus mx. But you know, in general, the mass of the daughter nucleus, that is this capital Mx, is much larger than this q over c square. And if this capital Mx is much greater than Q over C square, we can neglect this Q over C square in with respect to this capital Mx. So as we know, this Mx is much greater than Q over C square. So we can neglect this Q over C square. And if you will neglect this Q over C square, you can see from here that this Mx plus Mx will be simply equal to My plus My. And so we can write this equation in this way. Therefore, this Mx plus Mx is equal to My plus My. So you can see, let us see that this equation is, let us say, 1. Now again from this equation you can found that this My plus My minus Mx will be what? You can see from here that this will be actually equal to capital Mx. So now let us make the use of these equations 1 and 2 in the equation which we have just found for the threshold energy. And in this equation you can see that in numerator there is My plus My, which can be written as Mx plus Mx, and in denominator there is My plus My minus Mx. So you can see this may be written as Mx. So now the expression for threshold energy defined in equation B can be written in this manner. So we can write equation B as, how we will write it? This will be actually Ex Th equal to minus Q into Mx plus Mx over Mx. So you can see from this result that the threshold energy has been expressed in terms of the mass of the parent nucleus, that is capital Mx, and the rest mass of the projectile, which is small mx. So this is actually the threshold energy for theta equal to 0. You can say this is threshold energy for theta equal to 0. Now actually our aim is to find the threshold energy when theta is equal to 90 degree. But before that, let us see the threshold of the reaction product particle first emerge in the direction theta equal to 0. And now we know the expression for root over Ey, and from that we can find the value of Ey in this condition. So now we know root over Ey is equal to what? This is actually equal to P plus root over P square plus Q. You have seen that we have discarded the minus sign here because to start the nuclear reaction there should be only one value of Ey, and for that there is only plus sign in this expression. But you know, when the condition is of threshold energy, in that condition this term P square plus Q is actually equal to 0. So in condition of threshold, so you can say at threshold this P square plus Q is equal to 0. And as we know, this P is also 0, and so we can say from here that this Ey, root over Ey, this will be actually equal to simply P, because P square plus Q is 0, and so root over Ey will be equal to what? This will be simply P, and this implies Ey is equal to P square. Now you know the value of P, and this P will be when theta is equal to 0. So now substituting the value of P in this expression, we will find that this Ey is equal to mx into my into Ex at threshold condition, and over my plus my whole square, because you know in this condition actually theta is equal to 0, so cos square theta will be actually equal to 1, because the expression for P contains cos theta, so P square will contain cos square theta, but that will be equal to 1. So this is the value of Ey in threshold condition. Now as the bombarding particle energy, which is actually Ex, will be raised, the product particle Y begin to appear when theta is not even 0. So theta will also so the particle will appear in different directions for different value of theta when Ex is raised from its value when from the threshold value. But it means when Ex increases from its threshold value, then in different directions actually the emergent particle appear. Now let us detect the emergent particle in a particular direction, which is actually the direction in a perpendicular direction to the incident particle. It means we will now take theta equal to 90 degree. So now let the energy Ex of the bombarding particle is increased so that the emergent particle appears in a direction theta greater than 0, and we will take a particular direction which is theta equal to 90 degree. We have to observe the emergent particle in a direction for which theta is equal to 90 degree. So now you can see when theta is equal to 90 degree, then actually what will be the value of P? You can see it from the expression for P. You know the expression for P is what? This is actually root over mx into my into Ex into cos theta, but here we have taken theta equal to 90 degrees, so this will be cos 90 over my plus my, and since cos 90 is 0, so this will be actually equal to 0. So in this condition, this P is actually equal to 0. And so the expression for a square root of Ey will be what? You know this square root of Ey is equal to P plus root over P square plus Q. But in this condition, you have seen that this P is equal to 0. So this will be simply 0 plus root over 0 plus Q. And so this is simply equal to root Q. That is, we can say this Ey is equal to Q. And we know the value of Ey and not Ey but Q. So you can find the value of Ey. You know that this Q is equal to what? This is actually equal to Q into My plus My minus Mx into Ex when theta will be equal to 90 degree and divided by My plus My plus My. Now we know that actually at the threshold condition, this P square plus Q is equal to 0. And if theta equal to 90 degree, then P is also 0. So actually in this condition, we can say that this P square plus Q root over Q is actually equal to 0. And so if Q will be 0, then this expression will be 0. You can say that as in threshold condition, we know that this P square plus Q is equal to 0. And if theta is equal to 90 degree, then you have seen that this P is equal to 0. And therefore we can say that this 0 plus Q will be 0, which implies that Q is equal to 0. So now let us substitute the value of this Q. But when theta is equal to 90 degree, then what is Q? You can say that this will be QMy plus My minus Mx into Ex at theta equal to 90 degree and over My plus My is equal to 0. And so from here we can easily find the value of Ex when theta is equal to 90 degree. You can see from here that this is QMy plus My minus Mx into Ex at theta equal to 90. This is equal to 0. And so from here we can find the value of this Ex when theta is equal to 90, and this will be what? You can see from here this will be simply minus QMy over My minus Mx. My minus Mx. So actually this is the expression for the threshold energy when theta is equal to 90 degree. So this is also a very important result because in experiment The detector to detect the emergent particle is normally set in the direction at 90 degree to the direction of the incident particle. So this is as I have told you, this is threshold energy for theta equal to 90 degree. So in this way, in a set of 3 lectures, we have clearly discussed in detail the kinematics of the nuclear reaction, particularly the Q value of the nuclear reaction, and in detail the exo-ergic reaction and the endo-ergic reaction.